Hello, ladies and gentlemen. It's my pleasure to welcome you for this session. Today, we are going to talk about the most glamorous aspect of biological intelligence. That is, we are going to talk about neural intelligence or the intelligence of neurons. Now, this is one aspect which has inspired the artificial intelligence fraternity a lot. So, let me share my screen. So, today we are talking about neural intelligence mechanism. And this is the sixth talk of the series of 12. So we have already seen the basic cell intelligence, the biological hardware, the genetic intelligence, intelligence related to cell specialization, bioenergetics, mitochondria, and now today we are talking about the intelligence of neurons or the neuronet as it is called. So the human brain and nerves are made up of neurons, and this is how it looks like. This is a picture from some book. Okay, so without going into much detail about what is written in the fine print here, I just draw your attention to some things. That this is a star shaped cell with the nucleus in the middle. There is a central cell body, and there are many long processes or projections which are called as dendrites. Now these are primarily meant to receive input from other neurons. Okay, and or some sensors, maybe. uh, and then there is a thicker output process that is called as axon. Now it is like a long cable which has also in some sections the insulation to prevent the leakage. So these are the myelin sheath is supposed to provide the insulation, but in between there is insulation is stripped off, and those things are called as nodes of Van Weer, and where whatever signal is flowing through this output process gets amplified. It's like a relaying station to increase the strength of the signal through the longer length of the axon. Okay, so this is in a nutshell the neuron. So they have input signals coming from other neuron, and those signals mostly come at the branches, at the tip of the branches, in between the branches, or sometimes even in the crevices of the branches. Okay, so uh, and the part axon makes the nerves. The bundle of axons is something that we call as nerve in our usual language. It's a kind of insulated wire for longer distance transmission of signal, and where these intermediate relaying stations are there to restore the strength of the signal. Okay, to take care of the attenuation. So under some conditions, neuron is supposed to generate an output pulse of an ionic current, and that flows through the length of nerve or length of axon. Okay, inside brain, of course, there may not be this thing. There may be directly these things. These are called as synapses, the tips, which are connected as output. They are inputting certain dendrites for the same neuron or some other neuron. Okay, so these are the terminal fibers which carry the output, and the output is made available simultaneously at so many places. Not simultaneously, there will be, of course, some propagation delay depending on where this process is located on the length of axon. Okay, now so synapses are emanating from axon, and they relay the information that this neuron has fired. When it generates output, it is said to have fired. So we say that neuron has fired, means it has generated a pulse at the axon under certain condition. And yes, when the neuron fires after some propagation delay, that information is made available at all these processes at the tips, which are connected to several other neurons or possibly the same neuron also back. Okay, so when the pulse is generated, basically at the root here, at the axon hillock, this is called as axon hillock, at the tip of the tail, that is axon, the membrane changes the conductance towards the sodium and potassium ions in a short sequence like this one. First, normally it is at a resting potential, which is slightly negative. Then it becomes positive and then goes back again negative. So, due to change in conductances in that condition, it generates a pulse which is known as action potential. It's a standard pulse with fixed duration with fixed length. So the period is around 1 millisecond. Okay. The resting potential is around 70 minus 70 millivolt. Okay. It goes to plus 30 millivolt, and then again it depolarizes. It hyperpolarizes on negative side, and then after some refractory period, it comes back to the resting potential based on the ionic leakages, etc. So this is the output that we are talking, that it flows through the output of neuron or through the axon. Okay. So this is the action potential. This is the root cause of action potential. Under some condition, the conductances change, and then this pulse is issued through the length. And at the end, now these are the synapses. These are the terminal fibers, as we saw here. These get connected to various other neurons. Okay. So this is the boundary of other neuron. And as we know, all the cells will have some proteins embedded in their cell membrane. So also neurons will have, which act as some kind of walls, and conditionally by sensing certain presence of certain molecules, in this case shown as the red ones. Those are the neurotransmitters or the chemicals which are released by the synapse when the signal that it has fired comes here. So all these vesicles come and open out here, and they release certain chemical. Okay. Acetylcholine is one of them. There are many neurotransmitters. So those neurotransmitters open and close these channels, and then the sodium and potassium ions are taken through these channels in a bigger way, and they enter in the target neuron. So this is the signal giving neuron, and this is the output. This is the neuron where the signal is going, and this junction, there is a very small gap in between. It's a small cleft that is called as synapse. Okay. So if the synapse gets an information that action potential pulse has come, it releases neurotransmitter, which opens ionic channels of the connected neuron, and then through the media, surrounding media, the ions find their way into the target cell. Okay. So ions get injected. Now there are some synapses which are called as excitatory. There are some which are called as inhibitory. The excitatory synapses are the ones which, when they give output and the channels open in such a way that the ions flow from outside to inside, the positive ions flow from outside to inside, so that the potential inside goes towards the positive side. Okay. And then there are some uh, outputs, when they come, they inhibit, in the sense that they do the reverse. They will open these channels in such a way, depending on the properties of neurotransmitter that is there, that whatever ions may be inside the target neuron, those also get drained. Okay. Whatever positive ions were already there inside the target neuron, those will find the way out through these channels, and so the potential will go more toward negative side. Okay. Now whatever inputs are receiving excitatory synapse, when the input comes, there are chances that that target neuron could fire. Okay. Could generate also an action potential under certain conditions. So, and the inhibitory ones are the ones which reduce the chances of neuron firing. In other words, they prevent the neuron from firing. So that is excitatory synapse and inhibitory synapse. Okay. So a neural network, interconnected network, looks like this. There are several neurons. Okay. Each has its own one axon, and it is generating output action potential, and through the fibers on the tail of axon, the signal is made available as input to various other neurons. Okay, so that is the neural net. So output synapses from other neurons, also maybe from same neuron to same neuron. In that case, it is called as autosynapse. It could get connected as input again as a kind of a feedback, closed loop feedback, if you please. Okay. These interconnections carry tiny ionic currents of action potential, and they communicate the information. Okay. Now, inside the neuron body, remember this first slide. Yeah. Now, all these processes have literally the rivers of ions flowing. So, there are ionic channels, and depending on the branches and nodes, okay, you have a morphology of ionic channels within the neuron body. Okay, and that is what is deciding the logics inside. Okay, so typically this is just one illustrative case, that this is the axon hillock, the node 0 and 0. Now suppose at node 0 there are three rivers meeting, so it's amalgamation of b1, b2, b3, say branch 1, branch 2, branch 3. Okay, further branch 1 has node 1, branch 2 has node 2, this has node 3, and then there are further sub branches. So b31, b32, b32, b21, b23, b22, and again like that it can be cascaded along. So this is just a representative numbering scheme, okay, to designate the branches and nodes. Okay, now this could be used for when you want to simulate the behavior of a neuron on a computer, kind of a thing. So you have to simulate with the internal morphology, and for each neuron the morphology could be and would be different, certainly. Okay, so neuron will look like a tree with branches, with straight segment of branches, and with certain junctions, those are the nodes. Okay, so we can assume either we call it as an ionic tree, or we can alternatively treat it as an analogy of rivers, where each river has many tributaries. So many tributaries contribute to the river flow. Okay, and finally two or three or whatever number of rivers, they lead to one catchment lake. Okay, which is possibly having a dam. Okay, and when the water level in the catchment lake increases certain threshold, the gate of the dam opens. Now this is the analogous to firing of neuron. So whenever positive ions raise the potential of this node 0 beyond certain threshold, the gates of the dam open briefly, but the water is released in fixed quantum. It's not that continuous, it is just a pulse which is let out. Okay, so that is the action potential. So in pulses, in bursts, it drains out the level. Okay, and as many pulses are required to maintain the level, those many pulses will get issued one after another in succession, right? So this is how the neuron output will work. Okay, and of course these are all connected at the terminal ends. These are connected to output of other neurons or output of some neuron based sensors. Okay, so they will generate the output, and on the axon normally the outputs will go to some of these, but outputs of nerves will usually go to the muscle motor end plate, where when the output comes it will contract or relax a muscle. Okay, so it will carry out some physical action in the body. Okay, so usually the excitatory synapses will be on the long dendrites at the end of dendrites. Those are the ones which are usually excitatory synapses. Inhibitory synapses are generally at the nodes directly. So here there will be a synapse which will be giving a signal, and if this comes, it will block the effect of all these. Even if some pulses are coming here, its influence will be blocked here by the inhibitory synapse. Okay, so that is the excitatory and inhibitory synapse. Finally, all the flows, ionic flows, lead to N0, that is the axon hillock, and when the potential increases the threshold, action potential gets issued, and neuron fires. Simple. Okay. Simpler said than what can be mathematically represented. Mathematically, like in terms of engineering, if one has to represent each of these branches on a computer, on the software, in a simulation software, you have to use a model something like this. Okay, where this is the resistance of channel. So whatever ionic channel is there, whatever river is there, depending on its cross section area and length, will have certain resistance. Okay, so this is the flow resistance to ionic flow. This is the synapse. The synapse is coming at the base of transistor. Okay, so when the input comes from the power supply, that is the adjacent resource cells called as glial cells, neuroglial cells, the power is supplied and the ions flow, and they flow inside with some magnification. Okay, so this will have a magnification factor called HFE, usually in transistor parlance in electronics. So HFEE is the forward gain for excitatory synapse. So whenever an input comes, this is the multiplying factor with which the ions will flow inside. Okay, and they will have to counter this resistance, and ultimately the river will have certain volume, the channel will have certain volume, that will be represented by the capacitance or capacity of the channel. So it has to fill, and when it gets filled, its potential rises. Okay, and when its potential rises, that is given as the output on the output side of the link. Suppose we are talking of this link. So this was the input, this is the output side. That is close towards the N0 is the output side, and away from N0 is the input side always, right? So very simple. This is charge. This will hold the charge. It will hold the retain the information that some pulse had come here for some time. But of course, all channels will have some leakage. So through this leakage path, slowly that information will dissipate away. So if in quick succession you are getting pulses here, there are higher chances of this uh, going to elevated voltage and firing the neuron. Otherwise, if it is after delay, much delay, probably the effect of previous one would have gone down. Okay. And as I said, the inhibitory synapse will come at the output side. So it is somewhere here connected. Sorry, it is not showing connected, it's connected. Assume that it is connected. Sorry. So whenever input comes here, this is draining some ions from here. In other words, it is discharging this capacitor. Okay, and it is suppressing the chances of neuron firing. This is promoting the chances of neuron firing. This is suppressing the chances of neuron firing. So this is excitatory synapse and this is inhibitory synapse. Okay, and these are the parameters. I have not considered inductance, which also could be there. Okay, but for simplicity I have left out the inductance and just focused on the resistance aspect, right? So this is a simplistic model which one can use to represent each branches in the ionic tree. Okay, and the power supply, as I said, is neuroglial, the cells which surround the neurons. Those are the resource cells which provide ionic resources to neuron, so they act like a power supply. Okay, electronic power supply which will give positive and negative to the neuron. Okay, so each branch or limb could be modeled by having a table of parameters. So you have to substitute the values of all these in a table and you can model them. And then, of course, you have to tell the system which all inputs are there, where all pulses are coming at any given time in real time. So the input map for inputs, uh, synaptic input, has to be specified in the system. Okay, and then you have to multiply that with this amplification factor, etc. And then the charging of this capacitance with this time constant, that is time delay, propagation delay. So the information that this input has come here will be available here after some delay time. So there will be a delay. That's the charging delay of capacitance through this RC network. Okay, and that information will be retained for some time. After that, slowly it will get dissipated. Okay, so the channel leakage resistance decide the rate at which it is discharging or the previous information is vanishing. Okay, it has to vanish after some time. Of course, it can't stay there indefinitely. And this is the output side of the limb, and which is connected to a node or to N0, and that's how it is. So for each neuron, assume that this rectangle is a neuron. Okay, it has several synaptic inputs, say I1, I2, I3, I4, I6 to I16 possibly. Okay, and some of them are coming from its own output. So this is an autosynapse. Okay, that output is coming back here again, and inside it is some kind of a programmable logic array. Some years back, rather decades back, there used to be some devices in the market which were like ICs, like EPROMs, where one could interconnect various gates, AND gate, OR gate into configuration and build programmable logic. So neuron, in nutshell, works like a kind of a programmable array logic, and where the relation or the sensitivity that this input being present will fire the output or not, that sensitivity keeps on changing depending on learning. Okay, so that's the learning mechanism. We'll talk about it. So this is how the input map and output map is represented. These are the many outputs which are going. They will all carry the action potential, but maybe after different times depending on where they are disposed on the axon length. Okay. So IOs are designated based on the neuron ID. So you have to give the neuron ID number, some number, okay, and then output, then neuron ID, then the serial number, like that. Okay. So that's the one. And then you have to prepare a connectivity table for IOs, that which neuron, which output is connected to which input of which neuron. Now that's the connectivity table. And in real time, the IO status for all interconnected neuron has to be updated in every scan of software. I am assuming that the software is implemented on a regular computer, okay, as per the sequential routine scanning, like a PLC program or something like that. The electrical model of neuron is solved to work out the potential at the axon hillock, okay, based on the ionic tree, based on what potentials exist at the ionic tree. Okay, so and then you determine whether the neuron will fire or not by having a 0 or 1 status. It is digital, it is all or nothing. Inside, of course, there will be values which are in analog voltages, but output is 0 or 1. Either action potential is there or it's not there. It's a standard pulse. Okay, the simulation will model which input combinations from outside, because some neurons are, of course, will be interconnected as a cluster or as a neuronet or a ganglia is the plural. So as a group of neuron, as a bunch of neurons, uh, but there will be some inputs coming from the body, from the physical sensors of the body. Okay, and the outputs also, some outputs will also go to the muscles. Okay, so some outputs are executable, some are merely logic outputs which go to other neuron. Similarly, some inputs are coming from other neurons, so these are kind of auxiliary logic state, and some are coming from the ultimate sensors of the body. Okay, so under what conditions of ultimate sensors of the body some certain neurons are firing or not firing, that could be done by simulation, that could be simulated depending on this kind of software simulation. Again, I have talked about simulation of neuron body. Similarly, so this is each limb of that ionic tree, and this was the ionic tree for you. Okay, so similarly, the outputs also have to be uh, parameterized. So okay, it will have certain propagation delay, will have certain amplification which will result into action potential, will draw resources from surrounding cells and issue the action potential pulse along the length, and after different times that information will be available at synapse 1, synapse 2, synapse 3, and so on. Okay, so that's a simple model of axon. So depending on location of output on synapse, output synapse at the axon length, there could be some propagation delay. And expansion contraction of ionic channels also take place when there is action potential. The channel will try to expand, then it will collapse. So that exhibits sometimes some effects like inductance. So here I have shown the inductance. Earlier case I have not shown. It's okay, but it is also there, can be modeled if it has to be modeled. So at node of Ranveer, this is node of Ranveer. There is an intermediate amplifier which is boosting the power from resource cell, and it is again restoring the power so that the same magnitude of action potential propagates further because it will go on attenuating. Okay, so now if somebody has to simulate the behavior of interconnected neurons, a neuron ganglia, a neural network, you have to use certain tables, of course. So for example, there could be a table which is the real time simulated IO status come map. So this is a neuron ID, this is time, and these are the inputs which are coming. So this is a timestamp. So you have to always record the time spent. So it is assumed that there is a central clock which is giving you the time. So there will be a timestamp, and at that timestamp, what are the inputs? From where these inputs are connected and to which branch those are going, and what is the value of voltage there, and uh, what is the on the output side you solve the network, okay, based on the charging of capacitance and discharging of capacitance, etc. What is the output at the output side and what is the value? So what is the output, where is the output connected of that branch, and what is the value of that output? Okay, so this is one table. There is another table where of course you have to specify the morphology of neuron. So neuron ID will be there. Node N0 is connected to branch B1, B2, B3. Node 1 is connected to B11, B12, and like that you have to build the complete morphology table. Okay. Along with morphology table, of course, you have to record all the parameters of modeling. So HFEE, HFIE, that is inhibitory synapse and excitatory, and the resistance, leakage resistance, capacitance. Inductance I have not considered in this one, but could be considered. And you have to also carry one more parameter, which is the hit rate. That whenever some input came to this branch, okay, how many times it has successfully fired the neuron. Okay, so that is the hit rate, because learning takes place based on the hit rate. Something which is again and again coming and successfully firing the neuron, the probability of it firing the neuron in future increases. And conversely, something which has never succeeded in firing the neuron, the probability of it firing the neuron keeps on diminishing due to changes in the morphology. Okay, due to constriction of the channel size, enhancement of channel size, and so on. Okay, so there is a growth related with the usage, and there is a degrowth related with lack of usage. Okay, so based on that, all these values that we are writing here, they will have to be changed. Okay, and that is what will affect the learning. The neuron will learn due to changes in these parameters. It is based on the success rate, that how many times it has successfully fired the neuron. A particular branch, a particular node, a particular input, how many times it has successfully fired. Of course, other inputs will also be present simultaneously, but then we give that benefit of doubt. So whenever some input was involved and the neuron fired and that input was present, we give credit to that input, that yes, some contribution from that may have been there, depending on whether that node, whether that branch has led to significant increase in the potential of N0, right? So we work out based on the electrical network and we carry out the learning. Okay. Now, similarly, when the neuron has fired, we have to build an output table, that what are the outputs. This is a neuron ID, these are the various output at any real time. what are the values at different places, and we have to record what was the last time that it successfully fired, and what is the propagation delay for this and this, based on the model of the axon, right? So this is the axon modeling table. And then we have to have real time values for each node within the ionic tree. So n0, n1, n2, n3 with the neuron id. N0, of course, it will either fire or not fire. So we have to write the status whether it has fired or not. And N1, N2, N3, whatever is the value of potential, we have to write here. And then uh, the hit rate we have to update here as well as here, that what was the result, whether at certain time, certain input caused the neuron to fire. Now, if it has successfully fired, then we may have to edit some of these values after some time, not every time, but maybe after a certain period. If it is consistently happening, then we have to edit these parameters, because growth or degrowth of ionic channels will take some time. It will not happen instantaneously in real time. Okay, so it is a slower process. So learning is a slower process, so to say. Okay, so if the neuron fires, the output to its axon to be updated after respective propagation delay. If the neuron fires, you have to update the involved node and branch hit rate based on the where the higher potential is seen. Okay. Otherwise, if they were not used, they were ineffective, then you have to degrade them. So then also after some time, you have to edit these values and make them less prone to fire the neuron. So maybe this resistance will increase, this capacitance value will increase, leakage will increase, and so on. HFE will reduce, HFIE will increase, and so on. Right? So inhibitory will increase, excitatory will reduce. Okay. So all these parameters will together cause the neuron to go in a depression mode and it will fail to fire. Okay. And when the hit rate changes upwards or downward by certain percent, then you have to update all these model parameters to affect the learning. Okay, a certain thing is coming again and again and successfully firing the neuron, so probably yes, that thing has to be made more probable. You have to improve its probability of firing the neuron successfully. So that's how it works. And of course, there are physical IOs which are connected. This is a nervous system, and through vertebral column, you have. I'm not going into details of these, but they are connected to various fingers, wrist, various muscles. These are the outputs. Okay, various muscles at different parts of the body, and various nerves are represented to map in a different zones of the body, which are going out through these vertebral column. Okay, so this is the kind of biological IO map, so to say, which is connected to the human brain. So this is the IO map which is connected to the human brain. Okay, and some more of it, of course, the human nervous system. The picture is borrowed from public domain, thanks to the contributor who has put it. Due acknowledgement. I am just using it for reference for people to read. What if they want to read further, they can go to this thing. Okay, so these are the kind of muscles which are non-voluntary, for example, related to digestion, probably related to internal processes. Okay, controlling heartbeat, maybe saliva. Certain things are uh, maybe voluntary. For example, contraction of bladder is certainly voluntary. Sometimes it does become involuntary for some people, of course, but that's a pain. So these are the IO map, and likewise, which IOs are connected to which bunch of neurons in the brain. Suppose you slice the head somewhere here in the middle, take a cross section. This is how it will look like, and this is where the various parts of the body are mapped onto the brain. So these are the input side, they are the sensory associations. The inputs are coming to these physical zones of the brain, and outputs are controlled from this side of the brain. Okay, so which region will control what? Now again, it is statistically determined based on statistical study, that which part of the brain, if it gets damaged, what function is getting affected, and things like that. Okay, but uh, people know by now, of course, the brain association areas of which region of brain controls what, which is connected where. So that's the kind of IO map, as in case of any programmable logic controller or engineering electronic controller, you have input outputs, and where each input output is connected, one has to know. So this is analogous to that. Now, what leads to learning in biological neuron? When a synapse gets used often and when it succeeds in firing, its branch will get reinforced, meaning the synapses get higher amplification and those channel pathways become broader, faster, lesser leaky, so that it can fire relatively easy next time in terms of probability. Everything is, of course, statistical probability, but the probability improves. Also, if you assume that two inputs were there, and previously, if two inputs were ANDed, means if both inputs came together, then the neuron fired. Now, after many successes, they could get independently enabled to fire. So, ANDed dispositions will get transformed to odd ones. So, any one of them, any one or both, will be able to trigger the neuron. Previously, unless both are there or three or four of them are there together, then only they would fire. Okay. So, ANDs are getting converted to ORs with the success rate. Okay, and conversely also will happen that previously, okay, they were connected directly to n0, but they have not worked for a long time, they have not succeeded, so they will get ended. So they will only work when something else also is present. Okay, so it works both ways that way. Okay, excitatory synapses, when successful, they lead to physical growth, and hence generally those are located at the tip of dendrites, and those dendrites which are more successful will get thicker. So visually also one can make out which is more successful, which is more probable pathway, which is successfully firing the neuron. And inhibitory synapses, on the other hand, they tend to shrink the cell physically. Therefore, they will go into crevices and armpits, inside the branches. They will go inside because they keep on reducing the mass of cell wherever they are present. Yeah. Unused and unsuccessful synapses and pathways, sometimes they will get physically degenerated and eventually they may even get severed. So this leads to learning. Okay. And based on statistical history of successful firing of a neuron, the table of modeling parameters which I have shown you, ionic channels, get updated over a longer time frame, which will lead to learning behavior getting simulated on the computer. Okay, but the irony is we are simulating a group of neurons by a single computer, whereas each neuron is as good as one CPU. And actually, the human brain can be only equated to www, World Wide Web. It's not equated to one computer. So conversely, it is not possible to simulate the whole human brain in one computer. Okay, conventional computer. You have to have multiple CPUs interconnected through internet, etc. Those only together could probably simulate something like a human brain behavior correctly. Okay. So this is what it is, but our AI fraternity have oversimplified the whole thing, the concept of neuron. Now, according to AI, the neuron fires if so. In AI, they assume that all the inputs are coming directly to N0. That is, they are coming directly to the axon hillock. Okay, and all inputs are interchangeable. They are all independent of each other. Okay, which is far from being the case actually. Depending on in which limb, which branching you are coming from, the probability would depend on that. But here, what they simply do is to assign a weightage factor. So input 1 multiplied by weightage 1, input 2 multiplied by weightage 2. Now some of these weightages could be negative. So if it is inhibitory synapse, it will have a negative weight, right? So you just do a sigma of I1 multiplied by W1, I2 multiplied by W2, I3 W3, and In Wn. And together, if this sigma exceeds certain threshold, we say that the neuron fires. Simple. Okay. Being overtly oversimplistic. So where W1, W2, W3, Wn are weightage factors, and depending on history of success, you evolve the value of W1, W2, W3, W. Simple. Okay. So weightage factors, you transition the weightage factor depending on success rate. That is what will lead to AI or the learning part. Okay. So the value changes based on learning are driven by history of usage and their effectiveness. All inputs are assumed to be independent of others. So, but it is not simple addition based on series parallel connection of ionic tree. Within biological neuron, you have to, of course, see the morphology of ionic tree and do detailed modeling with interrelation of various inputs, which are ended, which are odd in the network, etc. One has to consider. Here, all that aspect has gone out of the window with the W factors. And in biological neuron, of course, there is also a propagation delay everywhere. For each limb, when the signal flows from one end to other, there is a delay. So you have to consider a delay. So based on that delay, there is a sequence factor, okay, which AI is failing to capture. So in biological neuron, you have to consider the propagation delay, the retention, the discharging of capacitor. So basically, what happens is that AI, in a way, is treating the whole neural intelligence as a combinational logic. I mean, it could have been more simple. You digitize and just assume it to be equivalent to a PAL, that is programmable array logic. You have just AND gate, OR gate. You are able to configure the gate depending on learning. Convert AND to OR. Simple. That would have been much hyper simplified case. Now it's not that bad in AI. They have taken cognizance of weightage factors at least, but and success rate based on that weightage factor, something they have done all right. But then they have not considered the interrelation between various inputs based on morphology, and they have not considered the propagation delay. At what will be the delay? So what input should come first? What should come later to make it fire? Okay, what is the interrelation? That aspect has gone. So this oversimplification treats neural intelligence as a combinational logic, whereas actually it is a sequential and combinational logic depending on morphological predisposition. Okay, so that aspect is seriously getting compromised in the present day AI. So some fun facts: neurons do not multiply after birth. We are born with the same number of neurons, and they are interconnected prior. So the interconnections are already there when we are born. Okay, so we are born with a fixed number of neurons, and neurons can only die. Interconnections were already there. Some of the interconnections may get severed depending on lack of usage. So that is what happens. Neurons generally do not cell multiply after the birth. So interconnections and predisposition start from as born state, and connections only get severed. Some connections may get reinforced all right, but new connections cannot be formed after the birth. Okay. However, yeah, I mean, biochemists can hoodwink the cells through chemical messengers like nerve growth factor, which make the cell believe that the body has still not been born, it is still under growth. So more neurons can probably cell multiply, probably. Okay, but normally it is not supposed to happen. The glial cells which surround the neurons, its role is less understood, but they form the so-called blood-brain barrier because the neurons have a negative resting potential, and if it comes in contact with the blood, its potential gets affected. So there has to be a blood-brain barrier to insulate the potential of blood from neurons. Okay, so Glial cells are the in-between cell which acts as a kind of blood-brain barrier. So they are insulating the blood from neuron, but they are carrying the ionic resources from the blood and they are making it available to neuron for all this generation of action potential and things like that, and synaptic inputs. So they, for all practical purposes, are analogous to power supplies, SMPS, if you please. Okay. So neurons are at different resting potential as compared to blood, hence glial isolation is required. So without glia, the neurons will not work. If you separate out neuron and separate out glial cell, neuron will fail to work, obviously. So although neurons are predisposed to assume certain specific role based on association areas that I have shown, but if some get destroyed or damaged due to some accident, other neurons can assume that role after some learning, which means that the hardware and algorithms are versatile and they are adaptive. So neurons can always adapt and form the team, and within the team allocate resources depending on what is available and what is functional and what is not. Okay, so there is a kind of a plasticity in neural behavior. Certain part of brain gets destroyed, the other parts substitute the function. Okay, so the last aspect is, of course, most interesting, the brain waves and their reversibility. Whenever we think, the human brain is in the process of thinking, analyzing, imagining, dreaming, or going in deep trance or hallucinations. The currents circulate in some loops within the human brain. Now, those can be smaller loop, medium sized loop, or bigger loop, and they keep flowing repeatably in certain kind of loops. Of course, in very small micron detail, one can't make out and decipher. But then from the brain, if somebody puts an electrode and senses the electromagnetic signals coming out, yeah, we get certain brain waves. Now they can be recorded on electroencephalogram as alpha, beta, and gamma waves. Okay, so the alpha waves emanate through the bigger circulating loops. That is, when the current inputs are circulating in a bigger loop, the neural currents are circulating in a bigger loop. Beta is in the medium sized loop, and gamma represents very small loops, almost like autosynapse carrying the feedback back to the same neuron. Yeah. So alpha, beta, gamma, these radiations or these voltages can be recorded from human brain when it is functional, and these effects are interestingly reversible. That suppose alpha is emanated when somebody goes in deep thoughts or deep trance. Okay, school composed person is going deep meditation, then he produces alpha. Now if somebody puts an electrode here and replace that alpha waveform, or it gives alpha stimulation to the brain has a tendency to go in deep trance. So it is reversible. So whatever is causing that wave, if that wave is put externally, the brain tends to go in the same thought process. That's the interesting aspect. So it is reversible. As alpha stimulation is a kind of meditation tool. Maybe somebody can artificially go in deep trance, or so. Similarly, if EEG is played back through electrode, it can cause certain thing. Certain neurons can be made to fire through this external simulation. Now, usually it is not very desirable because the effects are almost comparable with the narcotic hallucination or drowsiness which is produced through artificial drugs or something like that. So anyway, it's not a natural phenomenon. So not advisable to indulge. However, yes, technically it is possible. Good. So that's all from me for today. So I hope you have liked the talk, and in the next talk we will be talking further about some other interesting aspects of relation between mind and brain. Okay, what is the correlation between mind and brain? Okay, how do we think, how do we dream, how do we learn, how do we analyze, how do we synthesize information? and so on. Various processes in the human brain related to thoughts. Okay. So we'll be talking about it in the next talk. Till then, good luck. Bye bye. See you again.